Hello students, welcome to EPG Pathshala. I am Dr. Vishwanath Tiwari from Central University of Rajasthan. Today I am going to discuss a module that is kinetics of single substrate reaction, which include rapid equilibrium and steady state approach. This module has been taken from paper Molecular Enzymology and Protein Engineering. So, objective of this module is to understand the kinetics of single substrate reaction and steady state kinetics. So, this module is divided into following subsection. First, we will have a small introduction of enzyme kinetics, then we will have discussion of rapid equilibrium approach, then we will have discussion of steady state approach, and then we will discuss what is relation between rapid equilibrium approach and steady state approach. So, as you know, enzymes are the biocatalysts which have efficiency, a specificity and have mode of regulation. So, kinetic analysis can lead to a model for an enzyme catalyzed reaction, and which is important for principle of enzyme kinetics, which is used to write a velocity equations for an model which is tested by experimental approaches. So, when you are talking about single molecular reaction, that means here we are assuming that an enzyme is having only one substrate binding pocket. So, when enzyme combined with the substrate, let us say this is an enzyme, this is substrate, so they combine with each other and producing ES complex. And once the enzyme have the substrate in the active site, this substrate is cleaved into product and then product is released and enzyme is remain free. So, we have different rate constant that decides single substrate reaction. For example, the first rate constant is K plus 1. So, K plus 1 is a rate constant for the formation of ES complex, enzyme, substrate and its formation, that is K plus 1. The second rate constant is K minus 1, and that is dissociation of this ES complex into free enzyme and substrate, and K plus 2 is a rate constant which is responsible for breakdown of ES complex into free enzyme and product. So, K plus 1 is responsible for the formation of ES complex, K minus 1 is responsible for its back dissociation where enzyme releases its substrate, and K plus 2 is responsible for release of the product from active site. So, the formation of product is dependent on different kinetics parameter. Therefore, it is important to understand the kinetics of the single substrate reaction, and the velocity of single substrate reaction can be calculated by two ways. The first one is rapid equilibrium approach and the second is steady state approach. So, when you will understand this single substrate kinetics, you are able to understand how we can determine the kinetic parameter, how we will determine the product formation when an enzyme is using single substrate. The first approach of single substrate kinetics is a rapid equilibrium approach, which is also known as Henry-Michaelis-Menten approach. If you see the single substrate kinetics, so enzyme combined with the substrate producing ES complex with the rate constant of K plus 1, and ES complex is converted into the product with the rate constant of K plus 2. If ES is breaking back into the free enzyme and substrate, it has a rate constant of K minus 1. So in this theory, equilibrium theory, it is assumed that K minus 1 is very much greater than K plus 2. Therefore, if K minus 1 is very much greater than the K plus 2, there is more breakdown of ES complex into back into E and S, and we have less product formation. So when this condition is applied, there is establishment of the equilibrium between the formation of ES complex and its breakdown into free enzyme and free substrate. This also states that under rapid equilibrium condition, the velocity of the reaction at any time depends on the concentration of ES complex. So therefore, initial velocity, if the product is formed, so initial velocity is dependent on two things here. The first point is concentration of ES complex. The second point is the rate at which this ES complex is converted into the product, where K plus 2 is catalytic rate constant of converting ES into the product. So the velocity equation is V0 is equal to K plus 2 into ES. As the total enzyme which is present in single substrate kinetics is distributed in free enzyme and ES complex. So the total enzyme is equals to concentration of free enzyme plus concentration of ES complex. Dividing the velocity equation with ET, the velocity equation is written like V0 is equal to K2 or K plus 2 into ES complex. So equation become V upon ET is equals to K2 into ES divided by concentration of enzyme plus concentration of ES complex. If you see this equation, you can see that in left side we are putting total enzyme concentration, and right side we are not putting total enzyme concentration, but we are putting the representative of total enzyme concentration, where the total enzyme concentration is equals to free enzyme plus ES complex. So either we will write ET, either we will write E plus ES, both are the same. Therefore, in left side we have ET and right side we have E plus ES. But if you remember the assumption of equilibrium theory, ES complex can be expressed in terms of substrate concentration, free enzyme concentration, and dissociation constant. So the dissociation constant of a reaction where we have equilibrium between formation of ES complex and its breakdown is like a normal reaction when A plus B combine to form C plus D. So overall reaction is having a dissociation constant. So Ks is dissociation constant for that equilibrium, and it is represented by Ks is equal to concentration of enzyme into concentration of substrate divided by concentration of ES complex. If you rearrange it, then you can calculate what is the concentration of ES complex, and the concentration of ES complex will be equals to substrate concentration divided by Ks multiplied by free enzyme concentration. When we are substituting the value of ES complex into the equation, then you will have V upon ET is equals to K2 into ES is written. So we are replacing ES with its value, and that is substrate concentration divided by Ks into free enzyme concentration. So the equation becomes V upon Et is equals to K2 into substrate concentration divided by Ks into free enzyme concentration. Overall divided by free enzyme concentration plus Es is replaced by substrate concentration divided by Ks into free enzyme. So if you solve it, it becomes V upon Et is equals to K2 into substrate concentration divided by Ks into free enzyme concentration divided by 1 plus S upon Ks plus free enzyme. So what we did in the denominator in the right side, we are taking out E as a common. So E, if you are taking common, so E become 1 and the enzyme which is present along with the second part is taken as a common. So when you cross multiply denominator by K2, then equation become V0 is equal to K2 into Et is equals to K2 into substrate concentration divided by Ks into concentration of free enzyme divided by K2 in bracket 1 plus substrate concentration divided by Ks multiplied by free enzyme. If you cancel free enzyme concentration on the right side and K2 on the right side of the equation, then it become V upon K2 into Et is equals to substrate concentration divided by Ks divided by 1 plus substrate concentration upon Ks. If we know that V0 is equals to K2 into Es complex concentration, then K2 into Et is the Vmax because initial velocity is dependent on concentration of Es complex. But if all the Es complex is existing there, so if all the free enzyme is converted into the Es complex, then you will reach the velocity. Therefore, the initial velocity, that is V0 is equal to K2 into Es, can be replaced with Vmax is equal to K2 into Et, because here Et is equals to Es. So the maximum velocity will be observed when all the enzyme is present in Es complex form. So when we are replacing the value of Vmax in the above equation, then equation become V upon Vmax is equals to substrate concentration divided by Ks divided by 1 plus substrate concentration upon Ks. If you solve the 1 plus S upon Ks, then it is going to be equals to the Ks plus substrate concentration divided by Ks. After putting the value which is calculated above and cancelling the Ks, then equation become V upon Vmax is equals to substrate concentration divided by Ks divided by Ks plus substrate concentration divided by Ks. And if you cancel the Ks and Ks, then it equation become Vmax is like same and V0 is same, but in the right side it become substrate concentration divided by Ks plus substrate concentration. So overall equation, if you rearranging everything, you will find that the V0 is equal to Vmax into S divided by Ks plus substrate concentration. And this equation where we have V0 is equal to Vmax into substrate concentration divided by Ks plus substrate concentration is known as Henry-Michaelis-Menten equation that gives the initial velocity relative to the Vmax at a given substrate concentration. This equation is valid when initial velocity is measured over a short period of time so that the substrate concentration remain essentially constant. That means you have to perform this experiment multiple times, and this requires no more than 5% of the substrates to be utilized over the assay condition. So this Michaelis-Menten equation is a first equation which is based on the rapid equilibrium approach, and it is derived by Henry Michaelis-Menten, and it is based on assumption of equilibrium approach. After discussion of first approach, let's have discuss the second approach, that is steady state approach. This is also known as Briggs-Haldane approach. If you remember the kinetic equation, where enzyme combined with the substrate produces ES complex and ES complex releases its product, and K plus 2 is the rate constant of formation of the product, and K minus 1 is a rate constant of breakdown of ES complex back into the ENS. So, if we are assuming that K plus 2 is greater than the K minus 1, then there is no equilibrium between formation of ES complex and its breakdown back into the ENS. So, we will have production of products. So, if the concentration of the substrate is present in the saturated level, that means we have abundance of the substrate, and substrate concentration is very much higher than enzyme concentration. Then at any condition, we will always have concentration of ES complex static. For example, let's say we have 10 ES complex at a time. So out of 10 ES complex, if 5 is converted to the product, we will remain with 5 ES complex, but 5 free substrate are produced. That again combined with the substrate, because we have abundance of the substrate and producing ES complex. So therefore, if you see the change in the concentration of ES complex with reference to the time, then that is constant. So therefore, the steady state DES, difference in the enzyme substrate concentration, by difference in the time is constant. So DES by DT is 0. We have discussed about equilibrium approach. Similarly, we can derive steady state approach equations in a similar fashion. This steady state approach equation is given by Briggs and Haldane, and you know that in a steady state approach we are assuming that K plus 2 is very much greater than the K minus 1. Therefore, there is a steady state of ES concentration. So similar to the equilibrium model, it is known that the velocity of the reaction is dependent on two things. The first one is the concentration of ES complex. The second thing is rate constant that converts ES complex into the product. The equation is V is equals to K2 into ES. And we also know total enzyme concentration that is present is equals to enzyme which is free plus enzyme which is present in the form of ES complex. So when you divide initial velocity with the total enzyme concentration, then we will have the equation, and that is V upon ET is equals to K2 into ES divided by concentration of free enzyme plus concentration of ES complex. So if the ES complex is present in the steady state, then rate at which ES appear will be same as rate at which ES decomposes, because this leads to the steady states. Then we have to see how ES decomposes. ES decomposes by two means. The first one is by its breakdown into the product. The second means is its breakdown into free substrate and enzyme. So rate of formation of ES complex is K plus 1 into free enzyme into free substrate, and rate of ES decomposition is equals to K minus 1 into ES plus K plus 2 into ES. Why we are taking both here? Because there are two ways of ES complex to decompose. One via K minus 1 back into the substrate and enzyme, and other via K plus 2 into the free enzyme and the product. So if you take ES common from both, the equation become rate of ES decomposition is equals to K minus 1 plus K plus 2 into ES. As per steady state assumption, dES by dt is 0, or K plus 1 into E into S is equals to K minus 1 plus K plus 2 into ES. If you remember, left side of this equation representing the formation of ES complex, and right side representing the breakdown of ES complex. So if you solve it for ES complex, then you will find that ES concentration is equals to K plus 1 into free enzyme into free substrate divided by K minus 1 plus K plus 2. Three rate constant which is present here, you can see K minus 1, K plus 2, K plus 1. They are defined in term of Maclaurin constant, and that is Km. So the Km is equals to rate of breakdown constants divided by rate of formation constant. If you compare this Km with the case of equilibrium theory, in the equilibrium theory again the Ks is equals to rate of breakdown, that is K minus 1, divided by rate of formation, that is K plus 1. In equilibrium theory, when we are having Ks, we are not considering K plus 2 because we are assuming that in equilibrium theory we have less product formation, because as per assumption K minus 1 is very much greater than K plus 2. But here in the steady state approach, we are saying that K plus 2 is more than K minus 1, but still we are taking K minus 1 and K plus 2 both. So why we are taking K minus 1 here but not taking K plus 2 in the equilibrium theory? The reason is, when you are saying we don't have any product formation in equilibrium theory, that means you can ignore K plus 2. But when you are saying there is a product formation in the steady state theory, then you cannot ignore the reversibility of the ES complex, because no reaction is having 100% efficiency. Therefore, when you are saying Km, the breakdown constant upon formation constant, so breakdown constant include K plus 2, that is a main, but you cannot ignore K minus 1. So the Km is equals to K plus 2 plus K minus 1 divided by K plus 1. So you can calculate ES concentration. ES concentration, it is calculated in equilibrium theory where ES concentration is equals to substrate concentration divided by Km into free enzyme concentration. It is calculated in the similar fashion where we are calculating the Ks for equilibrium theory, where Ks is equals to enzyme into substrate divided by Es. Here it is a Km that is replacing that Ks. If you are substituting the value of ES complex, then equation become V upon ET is equals to K2 into S upon Km into E. Here we are replacing the equation V upon ET equals to K2 into ES divided by E plus ES. So we are replacing ES with S upon Km into E. And if you solve it, you will find that we have the final equation of V upon ET is equals to K2 into S upon Km into free enzyme divided by 1 plus S upon Km multiplied by free enzyme. When you cross multiply this equation with the K2, you will find that we have multiplication only in the denominator, and we will find that the equation become V upon K2 into ET is equals to K2 into S upon Km into E divided by K2 1 plus S upon Km into E. When you cancel free enzyme and K2, the equation become V upon K2 into ET equals to S upon Km divided by 1 plus S upon Km. We know that the Vmax is maximum velocity, and it comes when all the free enzyme is existing in the form of ES complex. So V is equal to K2 into ES can be replaced with Vmax equal to K2 into ET. So when we are replacing the value of Vmax in the equation, then equation become V upon Vmax equals to S upon Km divided by 1 plus S upon Km. And if you solve this lower part of right side or denominator of right side, you will have 1 plus S upon Km is equals to Km plus S divided by Km. After putting the value and cancelling the Km, the equation become V upon Vmax is equals to S upon Km divided by Km plus S divided by Km. If you further solve this equation, it become V upon Vmax is equals to substrate concentration divided by Km plus substrate concentration. And if you rearrange it, you will find that the V is 0 is equal to Vmax into S upon Km plus S. So what is Km here? So Km is Michaelis-Menten constant, which is dynamic and pseudo equilibrium constant, because we are talking about steady state here, so we are not having equilibrium. That's why it is pseudo equilibrium constant, expressing the relationship between actual steady state concentration rather than equilibrium concentration. After discussion of single substrate kinetics using equilibrium approach and steady state approach, we found that in equilibrium approach we have Ks, while in steady state approach we have Km. It is very interesting that Km is a Michaelis-Menten constant, but it is present in the steady state model, which is given by Briggs and Haldane, while Ks is present in equilibrium state model, which is given by Henry Michaelis-Menten. So we have to see what is relation between equilibrium model and steady state model. If you compare both the equation, you will find they only differ in the Km and Ks. So if you see that What is Km? So Km is equivalent to the substrate concentration that yield half maximum velocity, and it is related to different rate constants. And so the Km is equals to K minus 1 plus K2 divided by K plus 1. If you solve this, it becomes Km is equal to K minus 1 divided by K plus 1 plus K plus 2 divided by K plus 1. So if you are putting the value of Ks from equilibrium theory, where Ks is equals to K minus 1 divided by K plus 1, then equation become Km is equal to Ks plus K plus 2 divided by K plus 1. If we are assuming that no product formation take place in the steady state, or slow product formation take place, then K plus 2 can be neglected in steady state model. Hence, if you are having K plus 2 neglected, then Km become Ks. Therefore, we can say that Km is nothing but Ks, but when you're putting steady state assumption, that is product formation, and Ks is nothing, is a Km when you're putting equilibrium state assumption. So we can correlate in Km and Ks, or both equations, both models, equilibrium and steady state, with the relation of Km is equal to Ks plus K2 divided by K plus 1. So the main difference between two equations is Km and Ks, or you can say the product formation and product not formation, equilibrium and steady state. So students, let's summarize what we have learned from this module. In present module, we have discussed about single substrate kinetics. That means enzyme have a single substrate. So two approaches are used to explain single substrate kinetics. The first approach is rapid equilibrium approach. The second is steady state approach. And we have learned that how a rapid equilibrium approach is different from steady state approach. So in rapid equilibrium approach, it is assumed that K minus 1 is greater than the K plus 2. That means enzyme combined with the substrate and producing S complex, and they are going back into the free enzyme and free substrate. So we will have less formation of the products. While in the steady state assumption, we are assuming that K plus 2 is higher than the K minus 1. Therefore, the product formation is taking place and product formation is very fast. So you can say that in a steady state approach, the product formation is fast, while in rapid equilibrium approach, we are assuming that we have slow product formation. So if you see both the equation, the first equation, that is equilibrium approach. In the equilibrium approach, we have slow product formation, while in a steady state approach, we have fast product formation. So the steady state approach are more promptly used when your product formation is taking place fastly, while equilibrium approach is used when the product formation is slow, or product formation does not take place at all. We have few examples where product formation doesn't take place, but those examples are not there in enzyme kinetics. So when we are talking about enzyme inhibitor interaction, So, here inhibitor is homologous to the substrate, so they will combine with the enzyme and they can dissociate after some time, but they never converted into the product. So, when you are taking this type of example, then we will only follow equilibrium states or equilibrium approach. We cannot follow the steady state where the product formation takes place. So, both the approaches which derives the similar type of equation where V0 is equals to V max into S upon Km if it is a steady state, or Ks if it is an equilibrium approach, plus substrate concentration. So, when you compare both the equation, you will find that in equilibrium approach we have Ks, while in the steady state we have Km. And we have also seen that how Km is equals to the Ks. So, Km is equals to the Ks when we are putting the assumption of equilibrium theory into the steady state theory. So, therefore, you can say that equilibrium theory and steady state theory both are complementing each other, but they differ when you are talking about product formation. So, therefore, the understanding of single single substrate kinetics is very important, and they will help you to determine, to find out what are the different kinetic parameters that is coming out of these equations, these approaches, which will help us to understand the process of enzyme catalysis. Thank you.